is buffer solution. Okay, buffer solution is, it can be a mixture of weak acid and its salt, and it can be a mixture of weak base and its salt. Okay, and just now I took one example of weak acid. Okay, this is going to be the ethanoic acid. So I just tried to show you, okay, how do I get the salt? Okay, the salt normally it comes from, if you have the anions over there, this is going to be the anion for sodium chloride. So sodium chloride is salt. Yeah. So when I say salt of sodium chloride, yeah, NaCl. Yeah. So one example of salt involving this ethanoic ion is the sodium ethanoate. Okay, this is sodium ethanoate, but we write it down like this. Okay, most of the time it's always positive, then we write the negative. But in this case, it's a special case because I just want, most of the time they want to show negative and positive, the charges side by side. So if I write down NaCH3COO minus, the charges are very far apart. Yeah, so they don't want to write it in that way. Yeah, but it's still the same. Okay, it's still the same. So the one that I want to say over here is the salt. Okay, is going to be the sodium ethanoate. So how do I? You need to. It's a mixture. Yeah. So you don't expect that they are coming from the ethanoic acid itself, because it's a weak acid. If it is a weak acid, the amount of ethanoate is too little. Okay, so you still need to have external sources of ethanoate, and that is going to come from sodium ethanoate. So sodium ethanoate, how I write? Okay, it's going to be CH3COO minus Na. This is sodium ethanoate, and they will give you completely Na plus and CH3COO minus. Okay, this is going to be a mixture. Okay, this is going to be the buffer, the first example that they mentioned. Okay, so do remember, most of the what is important over here is, okay, the important part is, most of your CH3COO minus is actually coming from here. Okay, complete. Okay, it's coming from there. So that is going to be important. Another part is, okay, because when you dissolve or something, the dissociation is too little. So there is going to be a lot of this also. Okay, you need to remember. And this concept is going to be very important when it's going to be behaving as a buffer. I'll just show you one example, okay, how they will behave as a buffer. Okay, see, just now the same example, you see, yeah, ethanoic acid, okay, and then you have the sodium ethanoate. Yeah, you can see. Okay, they have written. Yeah. So now, okay, using this situation, okay, let's say I will write it down here. Okay, you see again CH3COOH. Okay, they will give you CH3COO minus H plus. The amount is little. Okay, the amount is little. Most of it is going to come from CH3COO Na, which is going to be, because it's completely it's a salt, so they will completely separate, cannot focus. Okay, CH3COO minus and then Na plus. Okay, most of this ethanoate is coming from the sodium salt of ethanoate. It means it's coming from here. Okay, it's coming from here. So now, okay, in order to behave as a buffer, okay, buffer means it's going to maintain the constant pH. Okay, when there is going to be H plus is being added, or OH minus is being added. So let's say now I'm going to add H plus. Okay, let's see what will happen. Okay, so let's say, for example, in this buffer solution, okay, this is a buffer solution, right? I am going to add small amount of H plus external. Okay, it means I'm adding HCl, for example. What will happen? Okay, what will happen? So I know that this H plus, okay, this H plus, they need to be removed. Okay, they need to be removed. How will they be removed? Okay, you can just always remember, focus only on the part that is having the reversible reaction first, because that is the part that we learn about LCP. Okay, when there is an increase of concentration or something, they can remove it. Yeah, they can remove it. So don't get confused with this one. This one just standby only, standby. Okay, you don't actually think about anything. Yeah, I'm just teaching you how to see. Yeah, how to see. So you focus only on the first equation. When there is going to be H plus being there, okay, it means you know concentration of H plus is being increased. According to LCP, okay, you need to decrease the increase in concentration of H plus. Dylan, how do you decrease that? By shifting the position of the equilibrium to the left or to the right? Still unmuted.
To the left.
Yeah, to the left. Yeah, so they will actually move to the left and they will try to form. Okay, in this case, I will actually show you certain things. Okay, when they move to the left, okay, what do you expect? Yeah, of course, the H plus is being removed, which is a good news. Yeah, it is going to be a good news. But while the H plus is being removed, okay, what will happen? This one will decrease. Am I correct? Okay, and at the same time, what will happen to this? They are going to increase. Okay, they are going to increase. So something will decrease and something will increase. Okay, now will the increase and decrease is properly compensated, or whether are they going to be covered properly? Like for example, I told you, if let's say, okay, Jordan have 100 apples, okay, and one of the apple, okay, is spoiled. Most likely Jordan will not notice that. Jordan, am I correct? Yeah, you won't notice that. Now, the decrease that happens for CH3COO minus, okay, is similar because there is a lot of this. Okay, just take it as this is going to be the 100 apples. This is one spoiled apple. Okay, so you are not going to able to see any difference. Okay, when there is a decrease in concentration of CH3COO minus. Another thing is, okay, remember you have 100 apples over here. Suddenly, Jordan, you have 100 apples, and then Kenneth throw you another one more apple. Yeah, and then suddenly you have 101. For you, will you notice that you have 101? Because the one is too little. Okay, the one is too little. For you, 101 is going to be still the same as 100. Okay, because why? Because there's a lot of this. Okay, that is the explanation over here. So what happens, okay, even though there is going to be a decrease of something, and even though there is going to be increase of something, the presence of, okay, the acid, the presence of the salt, okay, will actually make the decrease and increase not significant. Okay, so that is how buffer works. Okay, that is how buffer works. And you can read yourself. Okay, whatever that I mentioned about the apple is all written over here. Okay, it's all written over here. The position is shifted to the left. Okay, it will form more of this. Okay, so when I say a lot of apples, large reserve supply. Okay, large reserve supply, make sure the changes is not significant. And then large reserve supply of this, okay, make sure the changes is insignificant. So the pH, you cannot see any changes. Okay, that is going to be, it means that, okay, even though the H plus, okay, is changing and so on, okay, it will be compensated. Okay, why? The original situation is like, it's the same situation where you have that 100 apples, okay, nothing happened, okay, and then something comes in, this one is already been removed, okay, so something, it's like as though there's nothing happened, okay, as though nothing happened. So that is how buffer works, Okay, and if what will happen, okay, what will happen if I have, okay, if I have the same situation, but I'm using OH minus, okay, OH minus. So again, if I write CH3COOH, okay, if I write the same thing, okay, and then CH3COO minus and A plus gives you this. So now, when I add OH minus, do remember, how did I start earlier? I want you to only focus on the part that has the reversible reaction. Focus there only. Yeah, focus there only. When OH minus comes, okay, so what will happen? Okay, I know there is no OH minus here, there is no OH minus over here. So now, when you have OH minus, they will react. React with what? Early, they will react with what? Will they react with this or react with the H plus?
Sir, could you repeat the question?
Okay, when the OH comes in, okay, I told you to focus on this equation, right? Now, when the OH comes in, which part, okay, do you think there are three things over here, 1, 2, and 3. Which one do you think will react with OH minus?
The H plus maybe?
Yes. Okay, they will react with the H plus. Okay, remember this. Okay, this is very, very important. Okay, they will react with H plus, okay, to give you water. Okay, they will react with the H plus to give you water. So what happens over here, you see, the OH minus, okay, they combine with the H plus to form water. Okay, so what happens here, okay, when that happens, okay, the concentration, okay, of H plus will decrease because they are forming water. H plus is being used. Okay, so again, I have to ask Dylan. Okay, Dylan, what will happen? The position of the equilibrium will be shifted to the right or to the left?
To the left.
To the right. When H plus is going to be decreased, okay, you need to compensate. It means you need to increase the H plus. How do you increase the H plus? It will go to the right. Okay, your LCP. Okay, your LCP. So it means now your H plus is decreasing. Okay, and according to LCP, you need to increase the H plus again because I don't want the H plus to decrease because I want it to be the same. Yeah, I want it to be the same. So when that happens, okay, what actually happening is this concentration is decreasing. Okay, that concentration is decreasing. This concentration is increasing. Okay, to form more. Okay, so now earlier, okay, you have 100 apples, remember? 100 apples, and just imagine this is going to be 1. Okay, so when there is 1, okay, and then you have 100, okay, it still remains at 100. Okay, the excess, okay, the excess makes it that the increase is insignificant. Okay, and then how about this? Okay, you already have 100, okay, 100, and you lose 1. Okay, you lose 1. You will not notice it's 99. Okay, you will think it's 100. Okay, so it means that the increase and decrease is still going to be constant. Okay, why? Because the large reserve of this and this, again, same explanation. Okay, same explanation. That is, okay, explained over here. You can go through. Okay, I hope this is clear. Yeah, how buffer, yeah, how buffer works. So in summary, yeah, okay, maybe Davis can actually give me a summary. Davis, can you tell me, you have learned how buffer works and so on. What is important in buffer then? In summary, in layman's term, what is important in buffer? What you must have, what you must have in order something behave as a buffer? I'll try to answer this for you. Yeah. In order for something to behave as a buffer, remember when I add H plus and OH minus, I told you to refer to the equation that has a reversible sign. It means that you must have weak acid, okay, or weak base. Okay, I have discussed only weak acid just now. Okay, it means it must have weak acid and weak base. Now, in order to make sure the changes is insignificant, okay, you must have a large supply, okay, to compensate the changes. Okay, one of it is from the weak acid, no problem. But another one is the salt of the weak acid. That's why you need the salt of the weak acid. Okay, which is this one. Why? Because this salt will provide this. Okay, that is the same situation where you need the salt. Okay, the salt of the weak acid, the salt of the weak base. You need to have, in order for a buffer to happen, okay, you can have two types of buffer. They call it acid buffer, they call it base buffer. Okay, so whatever it is, okay, it must have weak acid, salt of the weak acid, weak base, salt of the weak base. Okay, now leads to another question. Can be buffer be formed between if you use HCl? Raphael, can you have buffer with HCl? Okay. Raphael, can you hear me?
Yes, sir.
Can you form buffer with HCl and
No.
NaCl? No. Why? HCl is not a weak acid. Can you form buffer with H2SO4 and Na2SO4? The answer is no. Okay, because H2SO4 is not a weak acid. Okay, that is very, very important. That's the crucial part of this lesson. Yeah. Now, so here, do remember, okay, there is a limitation. Okay, what is the limitation? The limitation is quite simple. Okay, if you have 100 apples, okay, and someone go and steal 50 apples from you, Jordan, will you notice? You will notice. If you have 100 apples and someone donated 50 apples to you, will you notice? You will notice. It is going to be significant. So there is a limitation. You cannot simply go and add any amount of acid and say the pH don't change. Okay, so we are always talking about a small amount. It can only the buffer can only compensate for a small amount, yeah, not for the big amount. So you see, no buffer solution can cope with the excessive addition of acid and alkali. Okay, pH will definitely change. Okay, if very large amount of acid and alkali are added, the pH will change significantly. So please remember that. Okay, so example, I've given you the example with apples. Yeah. So now, okay, if you look at this this mixture, like for example, this example here. Okay, just now I taught you about acid. Okay, acid buffer is easier to see. Yeah, easier to see. But now you see they say base buffer. Okay, so let's actually focus on the base buffer. So you see here you have ammonia. Ammonia is a weak base. Okay, ammonia is a weak base. How do I show ammonia is a weak base? Yeah, this one you must know how to write the equation. Okay, how to show ammonia is a weak base. Yeah, so in order to show ammonia as a weak base, you don't have any chance. You have to include water. No other way. Okay, this is how you show. And then it's a weak base, so it's a reversible reaction. And if it is base, what? They are proton acceptors. I hope you remember that. Yeah. So they are proton acceptors. So they will receive KNH4, H plus from water, and you will have OH minus. Okay. This is going to be the first equation. And do remember, this is the NH4 plus. Okay. Just now, remember the anion. Okay. So if it is salt, okay, salt of this, so now it's cation. Okay, it's a cation. So salt of this ammonia is ammonium chloride. I think you should know. Okay, ammonium chloride, ammonium sulfate. I think most of the time they like ammonium chloride. Okay, all ammonium salts are soluble. Okay, I hope you know that as well. Okay, so here they are going to give you, okay, NH4 plus, okay, and then Cl minus. This is going to be the combination of a buffer. Yeah, this is going to be the buffer. So now, okay, what we are going to explain over here is, okay, when you have, okay, a small the addition of HCl. So now you see HCl. What did I ask you to look? The first thing, look at the one that has the reversible reaction. Okay, this equation. You look at that. Okay, and then when you add HCl, okay, I think better to look at it when you add H plus. Okay, you add H plus. When you add H plus, okay, you don't go and add H plus with ammonia. Don't do that. Yeah, the H plus, okay, because they dissolve. Yeah, so you go and attack this one, like just now. Okay, you when you add H plus, okay, it will react with the OH minus, and it will give you water. Okay, and what will happen? Okay, if this is going to react, the OH minus will decrease. Okay, because it's reacting with the H plus. So according to LCP, okay, they need to compensate the situation. So Kenneth, what will happen to the position of the equilibrium? Will they move to the right or to the left?
Right.
Yeah, they will move to the right. During the time where they are moving to the right, what happens? You are forming, okay, more. I think forming OH minus, no issue, because that is what we want. Okay, we don't want any change, so it's no issue. But during that time, you are forming more ammonium. But this is no problem. Okay, imagine this is 1, this is 100. Okay, the large reserve supply of ammonium, okay, will make that increase of 1 is like insignificant. Okay, that is the same explanation earlier. Okay, and during the time that it is moving to the right, this is going to be decreasing, but no problem. Ammonia, okay, we assume that they have 100. Decrease of 1 is not going to be a big problem. Okay, that is going to be the explanation. Okay, and you can read through whatever I explain, how to put it in words. Okay, how to put it in the in form of words. Everything important are there. Shift to the right. Okay, concentration are too big. Okay, so it doesn't actually change. Okay, you just read. It's the same explanation. So make sure you know how to answer. Okay. Now, the next question is going to be related to sodium hydroxide. So let's say I erase this one. Same equation. Okay. When I add sodium hydroxide, okay, the best way to look at it is going to be by making just remove the Na plus. Okay, so you just look at it as OH minus. Okay, when you have OH minus, now, what did I tell you? You don't look at this. Always look at the part that has the reversible reaction. If you miss this step, you will get very, very confused. Yeah, you always look at the part that has the reversible reaction. And when I add the OH minus, what will happen? The OH minus concentration is increased. Okay, and what do I need to do, Justin? Shift the position to the right, to the left, not to the right, because the OH minus is increased. According to LCP, you need to decrease it, because I don't want that increase. I don't want that increase. I need to decrease it. The only way to decrease it is by moving it to the left. Okay, you move it to the left, and when that happens, OH minus comes back to the original situation. So no problem, that is fixed. But this is going to decrease. Okay, when that is decreased, you have a large supply, 100. Decrease of 1 is not going to matter a lot. The same thing, you are going to form a lot of ammonia. Okay, but I have a lot of ammonia. Increase of 1 is not going to affect, okay, the 100 of ammonia. Okay, that is, okay, coming back here. You read. Done. Okay, done. It's the same thing. So the next thing is, they say that explain why dilute aqueous ammonia alone will not act as a buffer solution. They say that why this one alone is not going to act as a buffer solution alone, yeah. So you see, when it is alone, okay, it means that I am going to ignore this. Okay, when I'm going to ignore this, what will happen? Let's see what will happen if we just look into this only. Some people will think, oh, I have the salt within the equation itself. Why I need to bother? Okay, can I just use this alone? Yeah, let's see. If I have H plus added, okay, when I have H plus added, this is going to be decreased. I need to increase it back. I will go and move to the right. Okay, so when I move to the right, no problem. Ammonia, okay, will actually react with water to give you ammonium, okay, small amount, no issue. Okay, no issue when it comes to H plus. But when you have OH minus, okay, when you have OH minus, okay, this OH minus will increase, okay. What will happen over here is the OH minus supposed to go to the left. Then there is a problem. What is the problem? Imagine there is 100 apple and there's only one person eating that 100 apple. Okay, one person maximum, how many you can eat? Okay, at one go, 5. Yeah. So there is not enough ammonium ion, okay, to remove the OH minus. That is the explanation. Okay, so whatever that is being added over there, it will not be removed, okay, by the buffer solution. So the buffer will not work. Okay, that's the explanation, and you can read. Okay, whatever explanation you see, ammonia is a weak base, equilibrium, they are not enough. This, yeah, basically, yes. They didn't mention about acid. Yeah, when it is acid, still can work. Okay, still can work. But not a buffer means, okay, they must work in all conditions. Yeah, cannot be just with acid, okay. Just with this, cannot. Yeah, cannot. Yeah, chemistry, I'm very good in stoichiometry. Just with stoichiometry, I can get good results. But organic or all this, I cannot do anything. So cannot like that. It must be everything. Okay, so a buffer must be able to remove both H plus and OH minus. I hope you can understand this. I think in detail, yeah, I went in detail. Okay, but now, okay, let's look at the calculation. Okay, calculating pH of a buffer solution. Can we calculate pH? The answer is yes. Okay, you can calculate the pH of a buffer solution, okay, by using the Ka. Okay, remember the Ka last time. Okay, I told you Ka, you remember H plus to the power of 2 divided by concentration of Ha. Why we have this formula? Because, okay, when I have Ha to change into H plus and A minus, okay, this concentration is the same as this concentration. Okay, but now, okay, it's supposed to be Ka equals to H plus A minus divided by Ha. Then only we came over here. But for buffer, we maintain this formula. Okay, we maintain this formula. Why? Because for buffer, the concentration of this is not the same as H plus. Okay, why? Because remember, HA to give you H plus and A minus, I need to have, okay, a salt of this. Okay, the salt, maybe I'll just put Ka. Ka gives you K plus and A minus. Okay, so this A minus, okay, is also going to come over here. There is going to be another assumption over here. When you use this formula, okay, very important assumption is I am going to take the H plus over here, okay, to calculate. I'm still going to take the HA over here to calculate, but the A minus, I am only going to take this A minus. I am going to ignore this A minus. That is the assumption. The A minus from the acid itself, I'm going to ignore. Okay, and some other assumptions such as the dissociation of HA is too little. I take the initial concentration of HA, similar to the one that we have learned last time. Okay, but the additional stuff over here is the A minus. I am not going to take as same as H plus. The A minus will come directly from the salt. Okay, so I'm ignoring the A minus that is going to come from the HA. It means that I'm ignoring the 1 apple. I'm just taking the 100 apple. I hope you can understand in that sense. Okay, I'm not going to count it as 101. I'm going to count it as 100. And I'm also going to count this as 100. I'm not going to count it as 99. I hope you can understand this. Yeah. So here,
It's like it's so there's so much of it that missing one wouldn't change it. Yeah.
yes, that is the
Okay.
assumption. Yeah, that is the assumption. And the same assumption we will use for applying to the formula. Okay. So the formula, okay, they have a separate formula used for that. Okay, we can come back to that. Okay, it's still, you do not need to know a new formula just to solve this. Okay, you can use the existing formula that you have already learned, and then just straight away you can solve this. Like for example, for this question, they say that calculate the pH of a buffer solution. They say the acid is going to be 0.6. Okay, and then the concentration of the salt, sodium propanoate, is going to be 0.8. So can I calculate the pH? The answer is yes. Okay, you see here, I'll just put concentration of the salt, okay, is going to be 0.8. Concentration of the acid HA is going to be 0.6. Okay, I'll just focus over here now. Now, first write the equilibrium expression, remember? Okay, just write down, okay, something H plus, then A minus, divided by the HA. Okay, the same. Okay, you write down. And then you are looking for, okay, this is Ka. You are looking for H plus, pH one. So what is, how to get H plus? This one times with this, divided by this. So you rearrange. Okay, H plus, okay, this one times with this, divided by this. Okay, rearrange. Now, you have the data for Ka. It's given. Put the data. Substitute, yeah, substitute the data. This is going to be the acid, concentration of the acid, initial concentration only, take 0.6, 0.6, divided by the salt, 0.8, take, put. And then you will get the concentration of H plus. Once you have that, I'm very sure you know how to do already. Yeah, pH is negative log H plus, and you will get the answer 4.99. This is by not knowing the formula. Okay, by not knowing the formula, you can straight away do. Okay, but there is a formula also if you want. Yeah, which is also you need to know for your syllabus. Okay, which is going to be just now. Remember, we add H plus. Okay, H plus equals to Ka times this and this one, right? So you see Ka, acid divided by salt. Okay, acid divided by salt. This is acid, this is salt. Okay, so you can simplify this into a formula if you want. Okay, if you want to just simplify, Okay, what is H plus? If I include negative log, it means everything I times by negative log. So negative log H plus, okay, negative log Ka times concentration of acid divided by salt. What will happen? Okay, if I times everything by negative log, okay, you will have this is pH. Okay, that's going to be pH. Your maths, yeah, I hope you learn this in your maths. Negative log Ka, okay, and then this is going to be still going to times, okay, so it's going to be negative, okay, log acid divided by salt, okay, and negative log Ka, okay, negative log Ka is going to be pKa. We already learned about pKa, okay, and then do remember here negative log, okay, negative log acid divided by salt, okay, here they change it into log 10 salt divided by acid. Why is that? Okay, because if it is negative, okay, if you want to change it into positive, okay, the other way around, then you can just change, okay, just put this for a plus log salt divided by acid. Okay, if you can follow, it's okay. Okay, if you cannot follow, it's still okay. Okay, in the end, you can still prove the formula. Okay, you can still prove the formula, which is going to be, if you want to use this formula, also can pH equals to pKa log 10 salt divided by acid. Very important. Okay, I remember SA. Okay, SA like strong acid. Okay, but it's actually like a salt divided by the acid. Okay, I think even in the past also I mentioned that there is a way to memorize the formulas. Yeah, so this one, if you want to remember that way, also can. Yeah, but if you don't want to memorize this formula, also can. Okay, no issues. Okay, you can straight away use the method that I taught you just now. So, like for example, okay, I know it's already 8:33. Okay, let me just finish this part only with you. So now, if you want to calculate the pH of the following buffer solution, yeah, so you see, you want to calculate, and in the internet also giving problem. Okay, but if you want to calculate, yeah, if you want to calculate the pH, okay, of the here this situation, okay, let me share the screen again.
Losing anything, sir?
Yeah. Don't leave first, yeah. Okay, don't leave first. Okay, give me about 5 minutes for this. Okay, so that later you can just discuss only. Yeah, no need to be bothered about this. Just remember the one we have learned just now. Okay. Ashley, can you still hear me?
Yeah, sir.
So here, okay, if you want to calculate, okay, you see you have the methanoic acid, sodium methanoate. So this is going to be the salt, and this is going to be the acid. Okay, there are two ways. I'll show you both ways also. Okay, if you want to use this method, like say for example, I know Ka, okay, equals to H plus and then the A minus divided by HA. So I want to find the H plus. Okay, H plus is going to be Ka times HA divided by A minus. Okay, Ka is 1.6 times 10 negative 4. 1.6 times 10 negative 4. And then the HA, okay, the HA is going to be the concentration of the acid. So 0.05. The concentration of the A minus, okay, is directly from here, right? So it's going to be 0.1. Okay, and you will get a value, okay, which is going to be this one. And then you can calculate the pH. Quite simple. Okay, quite simple. But okay, let's say if I want to use the formula, still okay. okay, you can still use the formula pH equals to pKa, okay, plus log, remember SA, yes, salt divided by acid. Okay, if you do it wrongly, then you will get a wrong answer. Yeah, so pH equals to pKa. So pKa, okay, this is Ka. You use the negative log, okay, 1.6 times 10 negative 4, okay, then you will get the value, and then you press log, okay, and then salt, okay, this is the salt 0.1 divided by acid, which is going to be 0.05, okay, and then you calculate straight away, you will get 4.1. Okay, this is going to be how you use the formula also. Okay, two ways, and I've shown you both ways also. Yeah, so of course, maybe later when during the class I will recall using this a bit, maybe for 10 minutes, and then users, okay, maybe 10 minutes I will just go through this and then we are done. Yeah, so it means on Friday we can just do the solubility product. Okay, so that's it from me today. Okay, so I'll see you again at 2:30. Yeah, see you guys. Bye.
Thank you,
Thanks,
sir.
sir.
Bye,
Thank you,
sir.
sir.
Thanks, sir.